ya sé que están asustados por la tarea y por eso no están llegando por aquí. Al final de la charla, hacia el final, entonces van a tener la oportunidad de presentar sus diapositivas y vamos a discutir. Entonces,
area of research that I'm particularly interested in. And we have some demos that we can go outside later and take a look under the sun. And then maybe the last 15, 20 minutes, depending upon how things go, I want the teams to come up and show a slide, or if you have them, or say something more about the idea. Okay? So that's our plan to end by 11 or so. Okay. Share something to say. Remember, you'll be great. So the title of today is Broadband Diffractive Optics for Spectrum-Splitting in Photovoltaics, and talk about what this is. I'm interested in increasing the efficiency of photovoltaics. That's the goal. And here, as opposed to yesterday, that we were trying to reduce the cost and allow thin film photovoltaics to work. Here, the idea is to use conventional photovoltaics, not just thin film, but the focus is on microphotonics or the optics, the nanophotonics, I guess. And we'll see what that is. So the motivation, of course, is the fact that you want to have widespread adoption of photovoltaics. You still need to reduce costs at the end of the day. That's the question. Okay? But as I said before, the goal of today's topic is to increase efficiency, not just to reduce costs. So the question is, how does the efficiency come into play when you talk about costs? Okay? And in order to understand that, it's very simple. You can look at the breakdown of the photovoltaic costs, okay? And a very coarse breakdown of it. Going into more detail, but this is enough for us to understand. We have three things to think about. One is the module itself, which is what we talked about yesterday. This cell, right? The cost of the silicon on the cell. So that's just this blue part. Of course, we have a big chunk of installation costs, which essentially means you have to pay someone to go on your roof, put everything on, and that's a labor-intensive process, especially in the developed world. It's expensive because someone has to not just install it mechanically, but also has to connect their wiring, to field code, all this stuff, make sure the environmental conditions are all met. Like that, right? So it's expensive. Turns out about almost the same expense as the module itself. Right? Kind of something people don't think about, but more recently, this has become very important in research. So there are lots of people are now thinking about how to make solar panels that can be easily installed. Okay, that's an innovation. It might not have anything to do with the panels themselves. For instance, can you make them such that it's plug and play, so easily plugged into some standard, so you install some standard rails, which are plug in very fast. There are lots of interesting things going on there. By the way, BOS stands for balance of system. Basically means all the other costs, which includes installation, transport, labor, anything which is not in those other three buckets. The last one is not terribly big, but it's important, is power electronics, essentially inverters and all that stuff. So of course, it's important because they have big losses. So if you spend more money, you get a better inverter. The other importance, excuse me, for power electronics is that every 7 years or so, the capacitors fail. Means you have to replace it. That's a reasonably big cost. Very expensive. So the question is, how does efficiency come into play here? You know, why am I showing this? Okay, if you think about this, okay, if I get a more efficient panel to a less efficient panel, efficiency essentially means that I'm producing more power with the same panel, same area. Okay? Now, if you think about these costs, all of these costs are roughly the same for the same area. Okay? Installation, transportation, roughly the same. Okay? So, with the same rough cost, if I can produce more power, obviously I can reduce the power supply. That's the logic. It turns out the efficiency has a multiplicative effect because it affects all of it. It's not just the module itself, which is what we talked about. Right? The efficiency can affect all these factors. So it's much more important. And actually, I would say the last 40 years or so, big effort of research to improve efficiency. Okay. And we can quantify how important is module efficiency. And this very important curve actually done by Ken Weaver, George Washington University class, very interesting class. Okay, this is dollars per watt, peak power, versus efficiency. And of course, you see a drop. More power, the costs are the same for different situations. So this is, starting for residential is the most expensive one because it's a lower volume. And then you have ground tracking, one axis ground tracking with on the ground, is what you're probably familiar with. And we have a few other things there: commercial tilted, commercial flat, and the cheapest one would be this non-tracking ground. Of course, CPV is not included. Concentrated. CPV could be even cheaper at large. But the key conclusion is basically down here. Okay, and this is the important thing to think about. If you have a 5% efficient module, which is free, costs nothing, okay, that is basically equal. You'll have to sell it at the same price, basically $3.50 per watt for a residential rooftop as a 15% efficient module costing $1.50 per watt. Okay, so in other words, if you have your efficiency is too low, the manufacturer of the panel will not make any money. You cannot charge anything for it. Basically, the calculation. Okay, which is of course a big practical problem because no one will want to manufacture. So efficiency is important not just to I mean, obviously efficiency is important because we can produce more energy from a smaller area, right? The environment is intact and all that. But also from a purely economics point of view, you need to have some minimum efficiency, otherwise manufacturing and the business point of view doesn't viable. You know, it won't happen, right? So this is from a few years ago. It has gone down. You can also plot it slightly differently, and it's useful to understand it this way as well, because if you look at your utility bill, this is what you see. You know, cents per kilowatt hour, typically. Kilowatt hour is the energy, unit of energy. And typically, few cents is what you get, what you pay nowadays, up to 10%. And you can plot that as a function of the module cost dollars per meter squared, which is the cells we talked about yesterday. A big contribution to the module cost. Now you can see different curves at different efficiencies. As the efficiency increases, the slope of the curve increases. Makes sense because that means small increase here will have a large change in module cost will result in a small in power cost, which is good for the person making the panel. That means the person making the panel can charge more, get a higher profit without causing his customers too much pain on the energy side. Okay, so higher efficiency is kind of good if you and you can look at how detailed this, but the economics by itself is very interesting. How the efficiency and the cost play in the picture, and this is something you need to think about. This is complicated, somewhat. Okay, now let's go into the technology. The thing to keep in mind is we need to understand why are solar cells not as efficient as glass. The main reason is a single band gap semiconductor does not match the solar spectrum. So if you look at the solar spectrum, it goes from about 300 more than a few thousand nanometers, and these are the fractions of energy in the different bands. Okay? So roughly in the visible, you have about half the energy. Above the visible in the infrared, you have about half the energy. Okay? Clearly, silicon is somewhere here. Somewhere here or so, and you're basically only collecting half the energy. Right? Okay, so let's try to understand this in a little more detail. Okay. Where does the energy go? It's easy to understand if you look at a simple cartoon picture of a semiconductor. You have a valence band, the conduction band. You have electrons, lots of electrons in the valence band, lots of available states or holes in the conduction band, which I assume you've seen last week. Your photon comes in. The photon, if it has enough energy, will kick the electrons out of the semiconductor bond and kick it. It becomes a free electron, gets to the conduction band, grabs it first. Okay? So if the photon energy is equal to the band gap, you have perfect absorption. That's ideal. In ideal case, of course, you never have perfect absorption. Then you kick an electron, you form the electron hole pairs, the electron goes to contact, another electron comes in, closes the hole, and get current. Okay? Straightforward. One problem, the first problem is non-absorption. If your photon does not have energy higher than the band gap, or its photon energy is lower than the band gap, the photon just passes straight through. Nothing happens. Right? This does not have enough energy to excite the electron, kick the electron out. And if you think about silicon, about half the energy gone this way. Because if you look at the spectrum, silicon band gap, let's say somewhere here, anything above this wavelength has less energy than the band gap. Just pass through, right? Lost. And that's a very silly way of losing light. Right? You haven't done anything to that. The other problem is thermalization. Thermalization happens when the photon energy is much larger than the band. Okay, in this case, as we know, quantum mechanics dictates that the electron then must be kicked out from a deeper level in the valence band, and of course it will get kicked up into a higher level in the conduction band. But that extra energy, unfortunately, we cannot grab it efficiently. The electron hole pairs, excitons, essentially have to undergo a scattering event because dictated by quantum mechanics that they have to lose that excess energy and relax to the band edges very, very quickly. Okay? Of course, there are lots of pathways that these extra energy and particles, the energetic particles, can lose energy. But the pathway that is the highest probability is what's called thermalization, where they very quickly relax to the band edges. That excess energy is essentially lost as heat in the crystal, vibrations of your crystal stack. And that's gone. Right? This heats up the crystal, which is even worse. Most semiconductor materials like silicon, as they heat up, they perform worse for a variety of reasons. So that's also lost, that excess energy. You still have this, and that loss appears, as you can tell, as voltage. Right? The band gap is this vertical axis is voltage. Right? And each electron hole pair creates current. And this, even though my photon had a high voltage coming in, high energy coming in, and if I could grab this electron hole pair, I would have gotten a larger voltage. But because of thermalization, my voltage has dropped across the semiconductor. Okay? The band gap determines voltage. Important. Voltage times current, power. It's not just the current, we have to also think about voltage becomes important. We also have another, of course, quantum mechanical effect of radiative recombination, which means that anything that absorbs light also has to emit light. And thermodynamics also dictated by quantum mechanics, which means that these electron hole pairs can recombine rather quickly and lose a photon, and of course, it's current. You can also have non-radiative recombination put down because you can avoid that by making your material perfect. So we can, the thing to keep in mind from this picture is that we can do something about these two laws. Okay? Everything else we can't quite do much about. Let's look at a little more detail about how the energy is distributed when it comes into the photovoltaics. It's a very important paper which was written 2 years ago by Harry Atwater and Albert Coleman in Nature Materials. Take a look at it. It's a very nice paper which talks about essentially the thermodynamics of losses in a single junction photovoltaic cell. Nice literature, but they're engineers. So this plot essentially where the energy goes. Of course, total is 100%. You start from the bottom. Conventional single junction solar cell can absorb something like 27 or maybe close to 30%. That's the absolute limit. You are an ideal 100% absorption. Okay? That's the green part. That's what you can get if you really, really work hard on making your single junction silicon cells perfect for gallium arsenide cells. Okay. The rest of the stuff are losses which most likely people don't do anything about. You just live with it. So you can see about 70% of the energy, most people don't do anything to try to grab it. Okay? So today we're going to talk about how to grab it. So let's go through it very quickly. The small bit here is essentially the entropy loss due to incomplete light trapping and reduced quantum efficiency. This is what we talked about yesterday. The light that goes in comes out. Basically, that's not trapped, or it just passes. It's just not appearing. Okay, we can do something about that by the techniques that I talked about yesterday, using nanophotonics. Okay, so, but that's not a huge amount, a little bit. It's still useful. You can do, there's an entropy loss due to the lack of angle restriction, which essentially means, and this is probably Professor Leandro talked about the greater case, you have a plus minus 0.25 degrees from the sun. Okay, but the re-emission from the solar cell, because anything that absorbs has to emit, is typically in a larger angle to increase the entropy of this. Okay, and that, of course, translates into an energy loss. You can try to reduce that, and that's harder to do, but there are photonic approaches people are looking at that. But again, it's not a huge amount, small amount, but it's still useful. And you can apply similar techniques like I talked about yesterday to adjust the re-emission probability as well. I don't have time to go into it, but we can talk about it later. This is the part I'm most interested in, because you can see that's the biggest part of the loss. That's almost 50%, right? Or really 40, between 40 and 50%. That's a big part, right? That's the energy loss due to thermalization or lack of approach. And that's the part I want to regain. And we can regain, okay, without going too much trouble. The other stuff, again, we can't do very much about it. We should be aware of it. We have an entropy loss due to non-reciprocity. Again, dictated by thermodynamics. I won't go into huge detail. You have an entropy loss in absorption or emission. And finally, you have an entropy loss due to the Carnot cycle, essentially the ultimate limit that you can get thermodynamically. In any case, if you're interested in, I would encourage you to go read the paper. Okay? But this is the part that I want to focus on. Okay. So, of course, this is this kind of analysis has been known. This is more detailed, but this has been known for about I would say 30, 40 years. It's not new. So people have tried to grab this part of the energy by making multi-junction solar cells, which you've probably heard of and saw this color. And I just picked an example. Okay? So the idea for the multi-junction solar cell is that this is a solar spectrum, is to essentially parcel out the different parts of the spectrum to different parts, different kinds of solar cells. So the blue part of the cell goes to the top Indium gallium phosphide cell. The green part goes to the middle Indium gallium arsenide cell. Okay, in gallium phosphide, gallium arsenide, you can adjust the band gap to going from arsenic to phosphorus. And the pink part goes to the germanium cell. Okay. The idea is that you split this out, then you avoided the non-absorption losses. In other words, the green photons will not be absorbed by the gallium indium arsenide. Sorry, indium gallium phosphide, the highest energy. Right? That would be a non-absorption loss for the top cell. But now by putting another cell which will absorb that, you can avoid that loss. And the same thing with thermalization. These blue photons, which have very high energy, if you try to absorb it with germanium, you will have thermalization losses. They will have very large energy and they will lose heat, right, because it's a small band gap. You can avoid that by just grabbing it in a different cell. And the way you do it is by stacking them vertically. You build them like a sandwich. Okay? At the bottom you have germanium. It's complicated, but very basically you have a germanium p-n junction. Forget this stuff for the time being. Okay? And then forget that, we'll come to that. And then you have indium gallium arsenide, and then you have indium gallium phosphide. They're essentially stacked on top of each other. The light comes in, the blue photons get absorbed here, green and red passes through, Green gets absorbed here, red pass through, red absorbed. Okay, so it acts as a natural filter. It's nice architecture. The problem is, as you can see, is that this is very complicated. A very complicated process, okay, for a variety of reasons. I'll only point out a few issues. But you can first of all see, the first thing to note is that germanium is extremely expensive, about 1,000 to 10,000 times more expensive than silicon. The germanium by itself, you start off with the germanium substrate, that's pretty expensive. And then you have to do epitaxial growth. Essentially, you would grow in high vacuum conditions, typically low temperature. You put down one atom at a time, one layer of atoms at a time, okay, from some source, atomic source. So you have atoms in a gas, vapor, right? You put down. You start with germanium, you put down indium gallium phosphorus in the right concentrations, essentially. Okay, and you have to build that up, and you have a hetero layer, buffer layer, tunnel junction, and so on. Okay, and the same thing happens here. Here you have to go from indium gallium phosphide to gallium arsenide and so on. And here you can see aluminum gallium phosphide and so on. So you have to have all these different sources. You have to have what's called a molecular beam epitaxial machine at very high vacuum. It's a very slow process, very expensive. Okay, so it's nice if cost is not an issue. It doesn't solve the cost problem. Okay, this, as Professor Mignano probably said, these kinds of cells are the ones that hold the world record. Okay, he mentioned yesterday that the world record was broken by sharp cell from Japan, and I think the record was 44%. He was mentioned yesterday to me. But a very high concentration, like 400x or so. So, but it's expensive. So even though you can get very high efficiency, and the way you get the high efficiency is by avoiding the non-absorption and thermalization losses. But even though you can do that, but it's at a very high cost. So that's why you can't buy and put them on your roof right now. These kinds of cells are what are used in satellites up in space, where cost is not important, weight is important. You don't have a lot of area. You only have a small area, and you need to produce lots of power. So then you go with it. Mars rover, the one in Mars, right? Probably they use the cells. This type of different versions. So the big challenges are, the reason this is hard to make is because we have to deal with what's called lattice matching. So remember we talked about yesterday, if you have crystal defects, then the charge electron hole pairs that are generated, it's trapped in the defect, and they don't reach your terminal to drive a current. So this is an example. Imagine this is germanium, and you're trying to grow, say, indium gallium phosphide. They have different lattice constants. This is different than this. So you end up with a little bit of a defect. You have 1, 2, 3, 4, 5, 6 germanium atoms. Up here you have 1, 2, 3, 4, 5, 6, 7 indium gallium phosphide, whatever. And they alternate. And you can see, because of that, you get this bending. Okay? You have the stress, and you have some defects. And this is where the electron hole pairs get trapped. You want to avoid this as much as possible. And the way to avoid this is by doing a very slow, high vacuum epitaxial growth. And that makes it slow, expensive, still complicated, okay? not terribly useful for low cost. The other problem, if you think about it, is current matching. So if you go back to our diagram here, you can see that's one cell, that's another cell, that's another, the 3 cells. They're all connected in series. If you think about these as batteries, the batteries connected in series. There's a problem with that. That means they all have to draw the same current. Exact same current, the series. Right? So what that means is that if you have 3 cells, top, middle, and bottom, they all have to have the same limiting current. But if you look at the spectrum, maybe you can match the blue and the green, but the red is very large. So the red current is typically the low band gap current, very high. So this extra current is essentially lost. And the reason it's lost is because you operate at a voltage, in the case of the low band gap, at a lower voltage, because the current is low. Higher voltage, that the current is lower. It's not operating at the maximum power point. I know 2 of you were working on maximum power point tracking algorithms and so on. In this case, you cannot independently operate all three cells at their maximum power point. There's no way, because they're all connected in series. They all have to draw the same current. Okay, in this case, you can only pick one current voltage. You can pick different voltage, but you can only pick one current. And that's picked here. That means you lost that excess. So overall, the overall potential of this technique is not achieved. Okay? It's still constrained by the fact that it is all connected. So to avoid this, and of course it's expensive. To avoid this problem, we started thinking, I mean, lots of people have thought about this. I put it as our solution, as I'll show you the PS, is to essentially design optics that will take sunlight and separate different colors, like a prism, 100 degrees, right? Or a grating or something like that. So like again, from a very simple perspective, sunlight comes in, we have some optic, which we call it a polychromat, and I have a few examples of them. We can go look outside later. What it does, it takes the sunlight, separates into, let's say, a pink, a red, and a blue band. The red on the left, blue on the right, and I pick solar cells to absorb them appropriately. So, for instance, I can pick whatever, germanium and indium gallium arsenide. Now, of course, the advantage, as you can tell, is that I can go from expensive multi-junction cells to less expensive single junctions. Would still be expensive. In my example, they're still expensive, but in principle, they can be cheap. Okay? And the cost of this, as I will point out, can be very, very small of the optics itself. That's also important. You want to make sure you don't increase any cost. Right? And you still get high efficiency if you look at the overall system. Okay? That's the idea. So let's see how we do. So we actually apply, let me jump back. So the goal here, in our case, was to design not just a prism or a grating. The problem with the prism, first of all, it's big. And also, you cannot control where the colors go in the prism, determined by the angle of the prism and the dispersion of the material. For a grating, that's the other option. The grating efficiency is very low. You can have a place grating at one wavelength, but the efficiency drops as you go. You can never get very high efficiency. But in our case, we designed essentially computer-generated holograms or computer-generated diffract ones. It's about in many different ways, where the idea is to design these geometries of these structures such that the different wavelengths of light diffract differently and end up at the right location on the solar. Okay. Now, the examples I'll show you are all one-dimensional, which means that these little structures are pointing out of the screen. They're lines. Okay? So the cross-section. And I'll show you some examples I have in demos. They're all one-dimensional. You can also make two-dimensional. One-dimensional is easier to make. The other advantage of one-dimensional is that if the sun moves this way every day, okay, the image does not shift. So that's acceptance angles in this direction can be the full day. Of course, acceptance angle this way is still limited by what the similar kind of system. Okay. So an example of a design is shown here where we take a cross section, and it's very complicated because it's designed using a linear optimization. But if you zoom in to a little bit, you can see what they are supposed to look like. They look like little staircases, right? Little structures. But they're multi-level structures, and they're complicated. Okay? And we pick these sizes to be something that we can fabricate easily. This is about 10 microns. Nowadays, the examples I show you, we've made them down to about 3 microns. And this height is typically in the order of total height of the order of 1 to 3 microns. That's small. And the whole thing in this example is about 1 centimeter. Okay? So not very big. Because our solar cells in this particular case was half that, about 5 millimeters. And the image, if you look at the image plane, looks sort of like this. This is the position, the one-dimensional image. Okay? So as I said, the idea is to separate the colors, right? So if you at every position, I can take a spectrum. So at every position, I plot a spectrum with this wavelength. And you can see the visible part of the spectrum is on the left-hand side, and the infrared part of the spectrum is on the right-hand side, primarily. So separated. You can call this essentially like a spatial spectral point spread function, or a response of this kind of an optic. Okay, and you will see this more often. Okay, so that's the thing to keep in mind. The idea is to put a solar cell over here, another solar cell over here. In this case, each solar cell is about 5 millimeters wide. The length, it doesn't matter. They're typically about squares, the ones I'm looking at. Okay. And you can also plot what's called the optical efficiency. And basically it comes from, this is a simulation, I'll show you some experiments. Basically, if you compute how much energy goes here for every wavelength as a function of the total collection area, and you can plot that as a function of wavelength, you get an optical efficiency curve. The blue curve is what happens on the left-hand side, the green curve is for the right-hand side, and you can average, you get something like 74%, much higher than what you can hope to get for a gradient. So in any case, we can, in principle, go much higher than 90%. Not the case. I'll show you some other results. So what we have to do, of course, is to make this first. We have to design. We designed this, but I showed you. Now we have to make it. Let me show you how to make it. Okay, actually, let me show you how they look like. So this is one of the polychromats that we fabricated. This is the bright field image. Again, you can see the little lines. Okay, it's about 1 millimeter this way, about 1 millimeter this way, and these are about 10 micron wide. This is the dark field image where you can see the different edges. Okay. And this is an optical profilometer image where you can see the different heights. They look like pianos. They're beautiful, actually. Look at it. And you can also look at the different levels. So typically the number of height levels, the discrete levels that we use to define those steps, determine how efficient they will be. Typically we go to about 16 or 32 levels. It's only 4 for illustration. Examples I'll show you more. How do we make this? We use a technique called grayscale lithography. And it's very straightforward, actually. What you do is you start with a piece of glass. Okay? Standard glass substrate. You spin coat photoresist on top, and typically you use a specific kind of photoresist that's calibrated for. Okay? To some thickness that is larger than the thickness that you're looking for. Then what you do is you come in with a laser pattern generator, essentially a laser beam, UV laser in this case. You focus down with the lens, reasonably high numeric value, spot size. In this particular case, 0 of a micron. Okay? And then by controlling the amount of energy we put down, we can control how deep the resist goes. Okay? So if I put a lot of energy down, after development, my resist is very deep. If I put a little bit energy down, after development, it's less deep. If I put very little energy down, after development, it's very shallow. Okay? And by knowing that the plot of energy, deposited energy versus how much depth I can access, which is essentially a calibration experiment, I can go from that to actually making what I want. So it's a little bit of a tedious process. There's a little bit of a process development part of it, which took us maybe about a year or so. But once you have developed it, it's relatively straightforward. So those different heights that you saw in this picture basically mean that here I put in more energy than I put there. This is standing up, and so on and so forth. As long as I know that conversion, it's easy for me. Okay. So once you have made it, you can also, of course, this is a more expensive process because you have to do this one by one. Okay, and I'll show you some examples, and I'll talk about this also at the end. We can go use this as a masker, and then take a mold of it. Okay, and then use that mold essentially to do stamping in either a roll-to-roll process or just stamping like you make CDs or DVDs. Okay? So it can be very cheap. So that's the principle shown here. The idea, we haven't done this. This is what we're trying to do. Actually, have a company that we're trying to manufacture. The idea is to essentially do roll-to-roll processes. It's straightforward. You come in with the film, you heat up the film, and here you have a patterned drum, okay, which basically has the pattern. You use that drum to press into the heated film. Relatively straightforward. The film cools, it maintains the pattern, and then it gets laminated onto some substrate. And then you end up with a parquet or an array of these elements on plastic glass. Okay. I'll show you some examples where we have actually stamped them. We haven't done the roll-to-roll process. We don't have that capability. So then, of course, the next step once you make it is you need to know what they look like. You need to characterize them. Okay? So the setup we use to characterize is I'm trying to think that maybe after this setup class, go out and take a look at my demo. But let's go through this, then you'll understand what you're seeing there. The setup is relatively straightforward. We have a lamp. Okay. We have to spatially, so this is, of course, the idea is to simulate the sun. Right? That I wanted to be able to make repeatable measurements, not have to take it outside all the time. So in this case, we let the light from the lamp basically expand, so you get highly spatially coherent illumination. Allows over several meters or so. And we have the polychromat over there, and then you have solar cells behind it. That's idea. So you can see it's a very simple setup. Just a mercury lamp. Nowadays, we actually use a superconducting source. This gives you much brighter, many more photons. As you will see, this current here is very low. Insolation is very low. So what we do is if you look at the polychromat, that's what it looks like. If you put a piece of paper in the back, you can look at the image, and this is what the image looks like. An example. First of all, you'll notice there are bands. There are one dimension. And there are three bands, three repetitions. The 1, 2, and 3. Because we made 3 unit cells. This, of course, the cartoon I showed you before is basically periodic. All the designs we do are periodic. Besides, we only made 3 for the sake of our demonstration. So you can see this is about a centimeter, the period. And the infrared bands are the ones that look dark. The visible bands are the ones that look bright. Infrared. And if you think about this, the concentration factor here, actually, can anyone tell me what the concentration factor is? That's a good you can discuss with your friends. So we'll all wait. I'm trying. Yeah. So think about what Professor Menon is talking about. He's talking about 400x concentration and stuff, right? So how many times have I concentrated? So let's go back to my cartoon. Get from there. Yes. This is not clear. Sorry, let's go back to I didn't draw that cartoon in the right place. It was really a cartoon. So think about this experiment. What do you think? How many times have I concentrated? Well, let's think about what 1 means. 1 means that my collector area and the solar cell is exactly the same. Right? No one. 1. Right? So here, I have concentrated somewhere. Right? So I've taken the light, my solar cell is smaller. They are bigger. But can you guess from looking at it? Maybe it's not clear from it. I'm not being fair. But I want you to just think about it. Wait a minute. No, not really. So the way to think about it is as the following. Okay, 1 unit cell here at 1 centimeter, 10 millimeters, is 1 unit cell. Okay, my solar cell is 5 millimeters. Right? So I'm taking it and concentrate it. Right. Okay. And if you think about this, I have 2 bands. I have to concentrate at least 2x, so I can put 2 bands next to each other. Right? If I don't concentrate 2x, there won't be enough room to put 2 bands together. This will be it's 2x. I'll go to more concentrations later on, but keep that in mind. Okay. Okay. So the next step, of course, we wanted to do was to put a spectrometer here and measure the wavelength, so we know exactly where the colors are. So it's very simple. We have the polychromat here. We have a spectrometer, fiber input on a scanning stage. And it's a one-dimensional image. So all I have to do is move one axis. This is done manually by micrometer stage. Nowadays we automate this stepper motor. Much easier to do. We have a little track to set the image. Then you can see, for instance, the image distance is quite large here, and the image distance can be determined by essentially the period of those lines that we saw. Okay, that's what defines the diffraction angle, right? From the grading equation. Sin theta is lambda over the period. So basically the same kind of as so we can make that smaller. We just use this just because it's easy to fabricate. And then we did the measurement. Let's see what the results. Okay, so these are the results. These are the same plots that you saw earlier, where you had the two bands separated, and these are the measurements. Okay. Again, at each position, we took a spectrum, moved over, took another spectrum, moved over, took another spectrum. And you can see they agree quite nicely with the same kind of a structure. You look carefully. There's a little bit of blurring, and that's because the fiber is not a point. Right? The fiber has some diameter to its input, so you can involve that measure. But you can see they agree quite well. The visible part is on the left, the infrared is on the right. Obviously, you see it on the card. So that's right. Nice to measure this. You can also measure the efficiency. So this is the simulation that we saw before. Thanks. And the measured efficiency is pretty close. Let me just think. Okay. So I think we should take a break here and take a look at the demos. How about that? And then the rest of the talk is short, but we'll think about how to do the electrical measurement with the solar cell. Okay? And if you want, you can go outside and take a look at these things. So I did very simple. We actually went one step further. We designed the object and the object actually take into account that some properties earlier that the extracts that those are designed to stop. But eventually what possible was that both integrated this logic and you can integrate both the electronics and the optics into a single model, so you can design these up. That's the idea here. So in this example that I'm going to show you, we use gallium indium phosphide, which has this blue external quantum efficiency curve, wavelength versus EQE, which EQE is essentially the probability that the photon coming in will get absorbed and form a current. Okay, so it's high probability for the visible photons. Okay? And gallium arsenide, which has something which looks like. Okay, so the idea is you want to capture this part of the spectrum for gallium indium phosphide at high voltage, and this part of the spectrum in gallium arsenide at slightly lower voltage. That's it. So the reference measurements were done. We have seen this before. Basically, for gallium indium phosphide, gallium arsenide, essentially we just use white light, simulated white light, not the sun. And you can see the current density versus voltage. The current density, first of all, you'll notice is very low because my insulation is extremely low. As I told you before. Same thing in gallium arsenide, gets slightly higher, gives a lower band gap, the photons. The current density is more than gallium indium phosphide. And if you look at the open circuit voltage, it is about here. Yeah, gallium arsenide is about a little more than 0.8. Gallium indium phosphide is a little more than 0.9. Okay, so the higher band. So the left-hand side, as a higher band gap, you expect higher open circuit voltage. Okay, so what do you do? So this is the design, again, not terribly important, but each cell in our case was 5 millimeters. Okay, tiny little squares, 5 millimeters by 5 millimeters. I don't make them. I got this from National Renewable Energy Labs in the US. So the collaborator there. And then we put them next to each other. So this is the design of the optic. This is 10 millimeters long, so I can put two 5 millimeter cells next to each other, exactly the same as the one you saw. But this is a little bit different. It's not the same design. In this case, they had 3 micron pixels and 64 height levels, so more comfortable, just to get higher efficiency. That's the idea. And this is the image, very similar to the one you saw before. In this case, it's flipped around, so you can see the visible part is on the left-hand side, the infrared is on the right-hand side, and it's the spatial spectral image of particular optimized particle. And the efficiency is very high because you have 64 height levels. The average efficiency is, about 10% higher than the example I showed you before. And you can see what it looks like visible on the left. Okay, so if you can take these simulations and actually simulate the electrical characteristics to see what you can expect to see. Okay, so that's what we did next. So we took the reference and then we simulated what we should expect to see with the ideal polychromatic. And in the gallium indium phosphide, you expect a huge increase in current density, short circuit current density, because what's happening is that you are redirecting the high energy photons, which are on the right-hand side, into the left-hand side. It's the gallium. So you have concentration, basically, 2x concentration, right? So that's why that increases. The open circuit voltage increases a little bit, as expected, also from the low concentration. I don't know if you talked about the effect of concentration on open circuit voltage, but it has a logarithmic effect. It goes with log of the geometric concentration. So you get a smaller effect. On the gallium arsenide side, the impact is smaller because gallium arsenide, being a low band gap material, already absorbs most of the photons. What the concentration only takes away some photons. The high energy photons absorb less efficient. Yeah, we'll see that later on this schematic. So the change here is much smaller. But overall effect, if you add them both, is quite large. If you look at the simulated power voltage curve, so there's power density versus voltage, the reference is shown there. That's a simulated increase in power, so that's pretty big. And gallium arsenide is smaller. If you add them both up, you get an increase to almost 28, which is quite large. A lot of percent to get 1 or 2%. Of course, this is just simulation. So let's see what actually. Experiments are not as good as this, obviously, so it's still pretty nice. So this is a fabricated polychromat. In this case, each line here is about 3 microns, about 3 times smaller than the ones I showed you before. And you can see the different colors which represent the different heights because this transmission optical phase difference gives us colors. And the measured spatial spectral image of the points per function is shown here. And you can see that this is the same plot as shown before. That agrees quite well. There's a little bit of noise here, but other than that, also here a little bit, but you get that. And you can also plot the efficiency, and the efficiencies are also reasonably close, so not that far off. And there was a small error in this fabrication because we did not know the exact refractive index here. So that affects the measurement. So this is the polychromat that we use, which is of course different than the ones we saw, a little bit stronger. And these are the cells. So we have a gallium arsenide cells here, gallium indium phosphide cells here, and we place them essentially like that. Measure current. You can see the contact. Pretty simple experiment. Okay. Once we do this, this is what we see under experimental conditions. So that's still the reference. Gallium indium phosphide does give you an increase, but that's the experimental results. Open circuit voltage increases, but short circuit current increases. Gallium arsenide also shows you an increase, a better than expected increase. Okay, and the part of this reason is because we did not redirect enough voltage. So gallium arsenide still is producing more power. Well, we can talk about that later. It's a little bit of a subtle reason, but both of them show an increase, approximately as expected. These are the measured power voltage curves. So this is the measured power. You can see the increase, and measured power for gallium arsenide again. This is pretty nice. And the total power increased by 16%, measured. Remember our simulation was 28. And the difference, actually, we spent a lot of time trying to figure out why is it so different. And it turned out, let me see if I have this. Yes. So to understand the discrepancy, we actually simulated the performance under the measured optical. Okay? In other words, we had the measured illumination that it's supposed to be, and then we used that measured simulation to measured illumination to simulate what the electrical properties should be. Okay, so in other words, if we wanted to get rid of any errors in the polychromat itself in the simulation. Okay, and you can see then the agreement becomes much better. So you compare these two curves, the solid line and the dashed line. They're closer. Close, not great, but close. Basically, that means that we think most of the discrepancy has to do with some fabrication errors and some errors in the refractive index. We did not know the dispersion of the refractive index was wavelength accurate. So nowadays we go to take much more care in measuring the refractive index and also much care in fabricating the So that is, and you can also look at the optical efficiency and relative close. And you can also compare it to the power. So the key points here, the measured increase in power is 16%, predicted increase in power is 28%, and if you get rid of any errors from the polychromat itself, the estimated increase in power is 22%. So they're relatively close. We think we understand most of the issues here. There's still a little bit of it. That's ongoing research. So the next question is, in the last few minutes, I want to talk about, what is the vision? What can we go with this kind of an approach? Can we go to very, very, very high efficiency? There was an important paper by Henry in early 80s, which talked about efficiencies of multi-band gap solar cells. It plotted as a function of the solar spectrum, in energy spectrum, the number of photons that are absorbed by the solar cell, and he has a very nice model which talks about this and so on. But the key thing is here. In this case, he used a concentration of 1,000 suns. But his prediction was that with a single band gap and 1,000 suns, you should get up to 37%, which is a little bit of an overestimation, but close enough. But the idea is that if you go to many, many, many more band gaps, he predicted that you can go very, very high, over 50%, which would be very remarkable if we could achieve that. 50% efficient solar cells. That would be pretty crazy. So we actually want to do this. The idea is to make many more bands. So this is an example of a design where we had 4 bands, 4 cells. And we think with 4 cells, with enough of a concentration, we can get close to 50%, not quite 50%. Like simulation example, we haven't made. The other interesting thing with these optics is that you can choose the number of bands and concentration independently. So in this example, you can see I have 4 cells, and I've concentrated them arbitrarily. More than 4x, but almost arbitrarily. Okay. In this case, I have 3 cells. This is the experiment that my students trying to do right now. We haven't finished this yet. We have a gallium indium phosphide, gallium arsenide, and silicon, and he's already designed and fabricated this, and just have measured them here. Okay. So here's a 3x concentration with 3 cells. But the idea is that now I can change the concentration and the number of cells independently, which means that I can combine cheap and expensive material. The most expensive material I will concentrate a lot, because I only need to use a tiny cell. The cheap material I concentrate less. I use big cell. I can combine this. That's impossible to do any other way. So hopefully we can optimize the system based on efficiency and cost. And this allows you the design freedom to do that. That's like you can think about a vision as a potential for very, very, very high efficiency. So in this case, we plotted the number of band gaps, okay, 2, 4, 6, 8, as a function of the overall efficiency. Okay. And the picture is like this. So if you have multiple band gaps, if you have n band gaps, you have n times concentration. That's in this geometric fashion. And you can see that these are the actual polychromat designs are shown here. This is an upper limit. And you can see potentially you can get up to 50% or even more, depending on how well you do the design, with maybe 8 band gaps. And I was talking to Professor Mignano yesterday, and there is a push towards 5 band gaps, which I don't know if we talked about, but and more. So in the next 5, maybe 10 years, we will see 5, 6, 7 band gaps as well. And if that happens in multi-junction cells, in principle, we can also make use of them. That it's easier to do with this because you get single junction. So the vision is to get very, very high efficiency. Yeah, that's a good point. So the other advantage, which we didn't talk about, is all these cells. So if you look at the picture that I showed here, if you look at this picture, I have 4 terminals of 2 cells, right? So I have, I don't have the other connections here, but I have 1 terminal here. Actually, I have another one here. I have 1 for this, and I have 1 for that. So I have 4 terminals. Each cell has 2 terminals. I can connect them however I want. In parallel, series, whatever, some other combination that's dictated by power electronics. I can do what I want, which is impossible to do with a multi-junction cell, which is automatically connected. So it's a very important point. In other words, I can operate each cell as its own MPPT, maximum power point. So that's an important point which I didn't yeah, so that's the idea. We want to get to very high, eventually, hopefully, to low cost. So the big challenge, of course, is also the manufacture. And I won't have time to talk too much about this, but the idea that we want to pursue, essentially, as I said before, some kind of a roll-to-roll processing, nano-influence, almost like CDs, but in a roll-to-roll fashion, like newspapers, plus some kind of a fast nano-patterning to make the original mold itself. Okay? And the example that you saw outside is basically this. We want to start with a photoresist master. You saw that. That was the one which was yellow. We want to basically make a PDMS mold, which is the floppy one that you saw. Okay, you put the polymer down, you bake it in an oven for an hour or so, and you can peel it off. And then you want to take that and then press it into a polystyrene under high temperature. Not very high, but enough to about 110 degrees to go above the glass transition point of polystyrene press. So that's the idea. The goal is to get low cost, scalable to high volume. You can in principle get high precision, and you can imprint into any transparent plastic. You use polystyrene because it's cheap, easily available. Eventually, like I said to some of you, I want to go to polycarbonate, like our glass buses fewer because it's much more resilient to bus. But, I think that's my last slide. So we'll stop here. I want you to, this was the homework for yesterday. I want you to take one idea and kind of think about how we improve it work and think about how we might do it better. Homework for today is, I want you to sharing the best idea. Homework for today, very important. So I want you to think about how to work it. First of all, the first question is to feel about it. And someone will buy with this buy yours. It's your idea that you come up with. And how much do you think they will take? And that's a hard, very hard question. How would you kind of work it out? How would you back think about these kinds of questions. How would you understand it? How much cost is how much paid for the buying and buy what would it take to get that delivery and again, not much. That's the goal of the one not even that it means you have to do this. You don't have another time. Today we have time. Okay, so let's start. So we have some time for discussion. My suggestion is you plug your own laptop in. Whoever wants to start first, fine.